Welcome to the 16th class meeting of EECE341, Introduction to Communication Systems. We will take the exam tonight from 7 to 10 p.m. and this will not be changed, okay? So you must be well prepared. You have to upload your solutions to the PLMS. Probably you need to handwrite to prove something and show something, and then capture the image and combine all of them together to a single PDF or some file, not multiple, single file, and you have to upload. Got it? So be careful. It's an open everything exam except any human interaction. So please don't cheat, okay? And homework is assigned already for class meeting 15, and today's class meeting also will be converted to homework and assigned. Today, I hope we may start chapter 4, but I'm not sure. I hope. By the way, probably next week, you will see the courses to be offered in the next semester, spring 25. And you have, I believe, mathematics for EE, and also you will see 2 of the communications and networking related courses, 3 actually. One is the Introduction to Digital Communication and Introduction to Digital Signal Processing, and also Introduction to Communications and Network. And if you are interested, then you may also take the graduate level probability and random processes. So you have undergraduate probability and random processes course and graduate courses offered at the same time. Some of you have already taken 302, so you may take 574. It will be offered as a full online course. So you can easily manage your schedule. Anyway, every time my message is simplify and visualize. And you found already from our textbook that some explanations related to coherent demodulator, sometimes we assume phase angle is 0. That is just for convenience. Phase angle difference between the received signal and demodulation carrier set to 0 for convenience. But you have to take the phase angle difference into account in many cases, and you will see some problems in the exam. Okay, so prove something, taking into account the phase angle. So be careful. As already mentioned, we are going to finish up this linear modulation technique chapter, and we are going to move angle modulation and multiplexing. And probably the pace will be like this: very slow, little bit fast, and very fast. Because especially about this 6 and 7, I didn't put the 302 material, 전자수학 A material, not as prerequisite for this course, which means that I'm not going to give you any probability related questions as far as it is a common sense. Because as a high school student, you all got high school diploma, and you learned what is a random variable. So I will talk a little bit about that, but not something like a Gaussian random vector, something like that. I will not talk about that. So it's okay, but anyway, fast and slow and fast, something like that. Okay? Here goes the review. In the last class meeting, I emphasized the image band problem. And this is one of the most important results you have to remember from the undergraduate introductory communications course, because this makes a lot of trouble, and you will see in the exam. Got it? And heterodyning was invented by Reginald Fessenden, who is the inventor of wireless voice, and he developed that idea to circumvent or overcome the technology limitation of his age. So it's like, given the IQ modulator formula, which is simply the representation motivated by the representation of real valued bandpass signal as a sum of the in-phase component plus quadrature component, right? And from that equation, it seems we need perfectly coherent, phase coherent cosine function and sine function. However, he considered, why not we use two stages to upconvert the signal? Because single stage, which is direct upconversion, was costly at that time, or impossible for high frequency, high compared to that period's technology. So he found mathematically equivalent formula. So first, generate sine cosine with low frequency, and that was possible at that age. And then he had an intermediate frequency real valued bandpass signal. And then what happened? He used single local oscillator whose frequency, if it is added to the IF frequency, becomes, for example, the desired target frequency. The problem is that since we are dealing with a real valued bandpass signal, the original IF signal has, in the frequency domain, has two components, in the positive frequency and negative frequency. This translates to the right side and also left side. So if you employ high side tuning or upper side tuning, you have to remove that lower side or low side. Got it? So you need bandpass filter or low stop filter if you want, something like that. So if devising that bandpass filter, implementing that is of lower cost than having a single direct upconversion filter, you adopt that structure. So that is one of the most important lessons we can obtain from the history or procedure or development of this heterodyne idea. And also, not only he invented heterodyne idea, he also, and some others, invented super heterodyne idea. What is that? In the receiver, we may do something similar. So in order to have a simple radio receiver, radio broadcasting receiver, which is tunable to your desired frequency, desired radio station, people adopted this super heterodyne idea in the receiver, where our channel select filter is fixed. So first stage mixer has a variable frequency, but this variable frequency translates all the desired signal every time to a fixed intermediate frequency, which is only passed by the channel select filter. That was an amazing invention. Anyway, in addition to this IQ modulator and demodulator, motivated by the representation of a real valued bandpass signal as the sum of in-phase and quadrature component, we may have other alternative formula which utilizes the amplitude and angle like this. So if this formula motivated IQ modulator, what about this one? That is the idea. So what we do is that we generate amplitude signal or sometimes magnitude signal, and we generate phase angle deviation. And by using this one, we generate that part, and using an amplifier that has variable gain, and that variable gain is proportional to this amplitude, we may construct a real valued bandpass signal. Actually, this is the idea of envelope tracking, sometimes transmitter, or sometimes, depending on our point of view, sometimes envelope tracking amplifier. Because this envelope tracking is mostly employed to implement amplifier in the transmitter. So sometimes some people say envelope tracking amplifier. Some people broadly say, hey, we have a envelope tracking transmitter structure, right? Or some people even say that this is polar transmitter. This is Cartesian transmitter, but it's rarely used, okay? Because this is something like real and imaginary, and this is Cartesian coordinate, and we have some angle and phase, amplitude and phase. This is in polar coordinate, got it? So there are many different names, but as far as you understand the fundamental, you can easily understand what your colleague or your counterpart talks about. I mentioned upper side tuning or lower side tuning in the transmitter, but that also occurs in the receiver. And finally, I talked about digitalization very fastly employed in the design, in the implementation of radio transmitter and receiver. So many parts has been converted to digital components. So if the analog signal, because we have an antenna for radio communication, which requires what? Analog signal, continuous time signal. So all digital components anyway needs to be converted to continuous time signal. If this continuous time signal is a baseband signal, actually two baseband signals in general, we call such a modem, modulator and demodulator, as a digital baseband modem. If our digital part generates or accepts in the receiver an analog signal in IF, intermediate frequency, we call the structure a digital IF modem structure. If the converted and generated signal, sampled or generated signal is an RF signal, then it's a digital RF modem. As you know learned from the sampling theorem, the technology required to implement this direction is huge. When I was an undergraduate student, it was just a dream. Okay, digital RF was a dream. Even digital IF was not that possible. So when I became a graduate student, some prototype transceivers were implemented this way, digital IF. And some of you are taking my Communications and Network Lab course, and our USRP, that is a software-defined radio, employs some model, especially the models you play with, employs digital baseband modem structure. So the digital part generates the continuous time real signal, baseband signal, and another continuous time real baseband signal. And there are two mixes, something like that. Got it? Now here goes the preview. And actually, even though, except this one, all these I repeated last time will appear in some sense in the midterm exam. So study very hard. Here goes the preview. We are going to wrap up the chapter 3, and the target is the early stage of wired telephony system. So in early 20th century, as you know, Alexander Graham Bell and some others, nobody remembers the second inventor's name, and invented the wireless wireline telephone. And it was spread very quickly. And if you are interested in history, this age, late 19th century and early 20th century, is called by many people the age of wonder. Okay? Some wonderful things occurred almost every day, every month, every week. Human beings started to fly. Human beings could send wireless voice. Wasn't it amazing? So every people wanted to have a telephone in their home. The problem is that how can we connect these two? Using a direct wire? What about two nodes or two vertices is now converted to million telephone service subscriber? Then, as you know, million choose 2, n choose 2 becomes very, very fast, increasing very, very fast, faster than ordinary exponential function. So people invented so-called star topology or star connection topology, where they have so-called telephone station. So here goes a central station, and these subscribers are connected to the central station. By the way, such a network, and also there is another central state far away, and it covers many, many subscribers. This is called wired telephone network, but usually these days called PSTN, Public Switched Telephone Network. As some of you already studied in the Introduction to Communication and Networks. Anyway, so as you see that, for example, in this line, initially only single subscriber had a connection directly to the so-called switch or exchange point. However, as the number of subscribers increased, there were too many wires. So so-called utility pole at that time called 전봇대 or 전신주, because mostly the wires were carrying telegraph signals, were now, at the time, started to being crowded by telephone lines. And saving the number of wires was very important thing. For example, suppose you have an apartment. At that time, there was no such a height apartment, but there are, for example, 50 houses, homes are there. Do we need 50 lines, paired lines? It's a waste of copper, right? So what do we do? So even the Thomas Edison was not the inventor of the wired telephone. He was an inventor who contributed a lot to the evolution of a wired telephone by inventing the method to put more and more subscribers into a fewer and fewer lines. And there were many ideas, but we are going to cover important ideas of doing multiplexing. Multiplexing, the term, is used in some area, in some sub-area of electrical engineering, like digital system, used in a different meaning. But here, multiplexing means that something like you put a lot of different signals into a single wire or single transmission medium, something like that. Sometimes it means you put many different signals into a single copper wire, some RF cable, sometimes putting within in a designated frequency band, something like that. And demultiplexing means that you take each one apart from your received signal, which is the sum of these signals. Got it? So we are going to study here, M means multiplexing. Okay? Some technologies related to methods for multiplexing, especially the emphasis is on pulse sorry, not here, multiplexing here, frequency division multiplexing, and also time division multiplexing, and some of space division multiplexing. Here, by the way, this is modulation. And this we will also study some modulation schemes like pulse amplitude modulation, pulse width modulation, pulse position modulation, but except the pulse amplitude modulation, all the other modulation schemes are nonlinear modulation schemes. So detailed discussion will be deferred until the end of chapter 4. Got it? And also, if we have time today, I'm going to talk about vocoder. By the way, vocoder is an acronym which is the sum of, voice coder, and coder means sometimes encoder and decoder. So voice encoder and decoder means is the meaning of vocoder. And vocoder is very important in understanding, especially here, chapter 10. As you have seen or you will see, information theory is related to compression of information and transmission and reception, of course, of information, and some security in communication and data compression and storing, something like that. Got it? So this may motivate you a lot. And the relation to the previous topics is that this is used for wireless digital voice communications. Okay. So our main discussion in chapter 3 and 4 are, you may regard, wireless voice. Okay. In the first chapter 3, it was wireless voice with linear modulation. In chapter 4, wireless voice in nonlinear modulation. However, as I emphasized, it's not all. Okay. Sometimes we really need complex valued baseband signal to be transmitted. And we've already seen some example. In SSB, even though SSB can be mathematically generated from DSB by subband filtering, mathematically speaking, alternatively, the SSB signal has what? Non-zero real part and non-zero imaginary part in its complex envelope. So it has in-phase component as well as quadrature component. However, just a simple DSB, you may say that just it has in-phase component, no quadrature component. So be careful. Here goes some discussion about pulse amplitude modulation. And I believe the author somehow misplaced this topic, because analog pulse amplitude modulation, well, I don't know how many people still use it, but anyway. So the idea is like this. As you see in that figure, suppose you have a signal that is a delta function delayed by n times t sub s. Okay. So in the time domain, here we have some direct delta function, which is scaled by some number m of nts. Here, you may regard m of t as your voice signal to be transmitted. And what does this mean? It's a sampled version of this one at time n times t sub s. So this height becomes this value. Okay? So suppose you have such a delta function. Then mathematically speaking, if you apply this delta function to an LTI system with impulse response h of t, that happens to be rectangular pulse with duration tau, what will happen? Your output becomes what? Your output becomes delayed and scaled version of this rectangular pulse. It has height m of nts and width tau, right? Now, we not only transmit this single delta function, but also transmit other delta functions obtained by sampling our, for example, voice signal. And what we do is that we transmit this impulse train. We apply this impulse train to this pulse shaping, so-called, this is called pulse shaping filter. Then what do we have? We have something like, where it is? Where it is? Yeah, something like this. Do you see this square pulse? Right? So we have m of t, right? And it is sampled, and it scales h of t. So let me give you an idea. So we have m of t, and that is sampled and delayed by ts, and we sum up all of them, and then we convolve with the pulse. And this is m sub s of t. By the way, if h of t, whose time duration tau equals t sub s, then we have this one. What if tau is smaller than ts? Then we have something like this, because each period ts is shorter than the duration tau, right? And also you can imagine the opposite case where tau is greater than ts. In that case, these pulses will overlap. And your instinct says that, oh, that's too bad. However, actually, there are many good waveforms that allows overlapping of these pulses in the time domain, but in the receiver, you can still retain the orthogonality among these pulses. You will be taught about those pulses usually in the graduate level communications courses. Got it? And definitely, I believe Professor Joseph John will teach that in the next semester's digital communications course. Okay, anyway, so this is a pulse amplitude modulation. Pulse amplitude modulation, as I told you, mathematically speaking, may have different pulse shape. Sometimes it's rectangular pulse with duration same as the sampling interval, sometimes shorter. Sometimes this pulse is a triangular pulse. Sometimes this pulse is Gaussian. Sometimes this pulse is sinc pulse. Sometimes this pulse is so-called square root raised cosine pulse. Something like that. So be careful. Pulse amplitude modulation. The original idea is to use rectangular pulse. It's no longer is the only definition of pulse amplitude modulation. You may employ other pulse shaping filters. Got it? Anyway, now what would be the character of this pulse amplitude modulated signal in the frequency domain? So the question is something like this. Suppose your message signal has bandwidth B in the baseband. Now, You do not directly use, for example, DSB family of modulation schemes or SSB or VSB. Just use first pulse amplitude modulator, and then you convert to, or you upconvert the signal. So the question is like this. Here is your speaker, for example. So you generate M of T, and here goes your A to D converter, which needs to be defined, but anyway. And here, what would be the spectrum of this signal? M of S of T after pulse amplitude modulation. An interesting thing is that it's very related to the spectrum of this pulse. And also the spectrum of M of F. The problem is that we don't know what is the message in communications. If otherwise, we do not need to communicate. Initially, in the first class meeting, I told you that why do we communicate? And answer was, there are many possible answers, but one of the answers was due to the imbalance in information. So if the message is already know why we transmit, which means that our message signal, even though after we observe, it would be a deterministic signal, but before we observe, in order to communicate, we need to model it as a random process. That's why this textbook has chapters talking about random signals. Without talking about random variables, random vectors, random processes, and random signals, there is no need to communicate. So some of you have seen the syllabus of this course without the 302 material, random variables and processes, and said, ooh, good, let me take it. It's okay, up to this 341. However, I guarantee that your digital communications course offered in next semester requires the knowledge in the modeling of random quantity, uncertain quantity using probability theory. So be prepared. Got it? Anyway, so let me just tell you what would be the spectrum, but actually power spectrum. And you don't know what it is. And power spectrum of M of S is proportional to the energy spectrum of the message if that is a deterministic signal. If it is a power signal, then you need power spectrum. And also the pulse shaping filters. Let me just use power spectrum. Okay. And you need to scale. You need to scale it. No, not here. Okay, something like this. So it's a product of the power spectrum of your message and the energy spectral density of your shaping filter. So your signal transmitted to the space using, for example, DSB, then what you have will be some product between sinc square, because this has spectrum, energy spectrum sinc square, right? If we square it, then you have some sinc square pulse like that, right? Yes, please excuse my wrong scale, but anyway. So you have sinc squared, and that is scaled by the spectrum of your message. So in general, your spectrum, your bandwidth is the maximum of the bandwidth, actually 2 times bandwidth of M of T and the 2 times bandwidth of h of t. However, is it maximum? Sorry, minimum, yeah, min. If we assume the speech signal is band limited, then after some frequency offset, we can say that the energy spectrum of the voice signal is 0, then 0 times some ripple of this square, sinc square is almost 0. So we are not occupying infinite bandwidth. However, we occupy significant part of the bandwidth. And this is the method to use pulse amplitude modulation, which is half digital and half analog modulation technique. And here, modulation means that actually conversion technique. So you convert a real baseband signal, in our case, the speech signal, to another real baseband signal. But it looks very digital, something like that. Got it? And then we may transmit using linear modulation technique. By the way, this A to D converter has some substructure. And as you learned in some courses, you may say that it consists of first the sampler, and second quantizer, and third encoder. And you need to know the function of each subblock. First, what is a sampler? Mathematically speaking, sampler is usually uniform sampler. Let me be careful. Uniform sampler with sampling rate 1 over Ts evaluates, mathematically speaking, evaluates incoming signals magnitude, let me say amplitude, which could be negative, at a uniform rate. So it evaluates the signal magnitude. For example, suppose this is m of t coming here. And uniform sampler with the sampling period Ts evaluates, which means that takes the values of this signal at a uniform rate. And the quantizer converts this possibly a real valued amplitude into usually a finite number, a number from a finite set. So here, suppose we assign 3 bits, which means that we have 8 levels that would represent the analog signal. In this example, if the sampled signal is within this interval, forget about the exact value at the boundary because it never happens probabilistically. So for simplicity, any value within this interval falls in this zeros level. We have 0, 1, 2, and 7 levels. So what about this one? This one is in the 3rd level. This one in the 7th level. This one in the 6th level, something like that. So variation within this interval is ignored. So we lose some information. So here, be careful. During quantization, we lose some information. Amazingly, our current state-of-the-art technology converts analog signal to a quantized level with many bits, like 16 bits. And how many? 16 bits means that you have this many levels. This is simply what? What is 2 to the 6? Around 64. So you have around 64,000, because 2 to the 10 is approximately 10 to the 3, right? And 2 to the 6 is per pi. Yeah. So around 64,000 levels. So these levels are very, how to say that, laser thin. So we usually, generally, human being cannot distinguish whether it is a quantized version or not if you assign enough number of bits. And what about this encoder? This encoder converts this name of level. Even though you may say that, hey, already we have a number, and this number is in binary representation 000, but sometimes it could be red, purple, red something, and blue, black, something, banana, apple, something like that, right? It shouldn't be necessarily a number. But in order to do digital processing, we need to convert it a binary number. And this encoder does what? Converts this level name to a finite number of binary vector. So here the zeroth level is now encoded here as 000. First 001, something like that. Okay? So in this way, this continuous time signal is now converted to what? A sequence of 3-bit discrete time signal, you may say, right? And even though we mathematically just view the output of the ADC as a discrete time sequence, but actually this is also a continuous time signal, precisely speaking, with finite levels, right? So for this one, sometimes people use encoding method, something like this. So at every TS, we have what? A sample. We have what? Quantization. We have 3-bit. So here, as you see, first 3 lines, actually it's a pulse here, very short period. And this dashed line means that no pulse. Okay? So in this case, probably this interval is 1/3 of TS. So at every TS of over 3, we have a pulse or not. If there is a pulse, it means bit 1. No pulse, 0. So here we have 0, 1, 1. So no pulse, pulse, pulse for the first TS. And then we have 1, 1, 1. That's why we have 3 pulses, something like that. This method is called pulse code modulation. So this was the first step in digital voice and audio. So we have an analog signal, and we have a stream of pulses, like silence, boop, 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 silence, silence, boop, boop, silence, boop, silence, something like that. Got it? And sometimes, in order to reduce the number of bits, people put more ideas in this digitalization. And one of the ideas is delta modulation. Delta modulation is an interesting idea. We just take out the difference between neighboring, adjacent 2 samples and encode the difference only. So suppose you have very slowly varying signal, but you have very fast sampler. Then you may assign a lot of bits to represent this height if this is slowly varying, and also may take a large value or may take a small value. But if it is slowly varying, the difference will be very small, which means that if you sample the difference between 2 sampled signals, originally sampled signals, you may save a lot of bits. That is the idea. So here goes M of t, and what you do is that you first, this part is simply say that you convert the signal to this form. Okay? So piecewise constant signal. And then you subtract. This is multiplication, but you may regard it, you subtract S of t from M of t, then you have residual. And then you may encode the residual only, something like that. There are many different ways to do this delta modulation. Delta means difference. Okay. So this is so confusing. Just regard it, not even this one. Just regard it. You sample the signal first, and you compute the difference, and you encode the difference. That is the idea. The problem of this delta modulation is that if you make an error in demodulation, the error propagates, right? Because from that, the difference will be added, added. So your error will be lasting for a long time. Anyway, so people wanted to save the number of digital bits when they convert the analog telephony network to digital telephone network. And that's what we talk about. By the way, in delta modulation, if we assign very small bits, then we have a problem. Because sometimes the difference may be over our bit resolution. In that case, we can only keep up slowly. For example, we may not represent this big jump with a small number of bits. Then our delta modulated signal will be reconstructed following this line. Then we have this error. So this is called slope overload, and we lose some information. So this type of approach should be chosen very carefully, depending on the nature of character of our original message. The problem is that our speech signal cannot be mathematically well modeled. That was the belief. But you will see what our human being have achieved to compress our voice. Anyway, as I told you, we not only have pulse amplitude modulation to half digitalize our speech signal, we also encode the sampled signal using pulse width modulation. And we've already seen some figure. Let me show you. Where is the... Yeah. So this is pulse width modulation. And even though you have variable width pulse, you may also regard it as it consists of very short pulses. For example, here you have 10 pulses, here you have 11 pulses, here you have 15 pulses, something like that. Even though for simplicity, we just vary the width of pulse, you may just say that there are very short duration pulse, and if our value is large, we send many pulses. But this period is fixed. It's similar to some bad habits of motor drivers. For example, some of my acquaintance, when I take his or her car in the assistant's seat, I feel vomiting, because if I would drive, I would push the accelerator pedal continuously to increase and decrease the speed. But my acquaintance does this one. So he or she, I do not reveal the... anyway, if wants to increase the speed, this way. So it's like pulse width modulation with a lot of pulses. And wants to slow down, then something like this. So these days, our motor vehicles are very sensitive. So every time I go together, then I sometimes feel this one. And the problem is that usually drivers do not know that because the driver know his or her action already. So the mind or our brain adapts to that pulsation. However, all the other passengers feel a lot of pain. Anyway, so pulse width modulation not only changes it could be implemented by varying the width of pulse, but also could be implemented or approximated by using very short pulses, but number of pulses within an interval is varied. Got it? And actually, for your senior design project, many of you will adopt pulse width modulation to control your boats, probably. That is the idea of pulse width modulation. Now, this pulse width modulation, you may say that may not suitable for voice encoding, but actually it well matches with a specific type of amplifier in the receiver. And that amplifier is Class D audio amplifier. So it's like this. Usually amplifier amplifies the input signal, right? But what if your amplifier internally has some circuitry that accumulates your incoming signal for a while? So it has some low pass filter and then amplify. It's similar to my acquaintance driving the car, right? So instead of pushing the pedal like this, you may do very quick pushing, and instead of slowing down, you may reduce the number of or even the interval of pushing the pedal. So this Class D amplifier turns out to be very suitable to amplify pulse width modulated speech signal or audio signal. And this Class D amplifier is very, very power efficient, which means that given the same driving amp power, it can generate very large signal. So some of you may remember there was a cell phone manufacturer, Korean cell phone manufacturer, who adopted this amplifier. Not Samsung, not LG, but it's Pentel. But anyway, this manufacturer had a product that has very powerful Class D amplifier. So even though the phone was very small, it was like you have a boombox. Anyway, so there are a lot of ways to modulate acoustic signal or speech signal or voice signal to convert it to a digital format. Sometimes some apparently weird technique well matches to some implementation method newly developed or discovered in the left side of the building of electrical engineering. So that's why I also emphasize that even though you have now decided that, okay, I will live in this right side of the electrical engineering building forever, but be friendly with your friends in the other side of the building or vice versa. Because sometimes your headache problem can be easily solved by just talking with your friend in the other side of the building. Hey, what's up? I have a problem, blah, blah, blah. Is there any new technology to solve this problem? Yes, we have, blah, blah, blah. Then, voila, you have a great invention. Got it? Now, here goes multiplexing. So suppose we somehow just use voice signal, analog voice signal, or we may have digital sampled or converted digitally modulated voice. The problem is that still we want to reduce the number of wires or cables for our telephony system. What do we do? First idea is frequency division multiplexing, which is actually used in the early stage of radio broadcasting. And idea is simple. As you see, this is a rainbow, and now you remember that red is outside. Actually, there is another rainbow, always double. We seldom notice. But anyway, so the idea is like this. In the frequency domain, you use different carrier frequencies, or simply sometimes different channels, different carriers, different bands, depending on your definition. So here is a signal from KBS, for example. Here is a signal for NBC. Here is a signal for SBS. There are some signal from CBS, something like that. So in the frequency domain, your signals do not overlap, or even though they overlap, they do not interfere much. That is the idea of frequency division multiplexing. However, some people define frequency division multiplexing as a multiplexing method that do not allow overlap. Some people. So you've seen, some of you have seen OFDM, that is orthogonal frequency division multiplexing. And this becomes weird because frequency division multiplexing in a narrow sense do not allow overlap. So which means that if you extend integration of the product of two signals in time domain or using Parseval's relation frequency domain as an inner product, and if it is zero, then you define orthogonality, then frequency multiplexed signals are always orthogonal, right? Then why we have this apparently redundant adjective in front of FDM? It is because some people do not define FDM as no overlap allowed. Some people say that, okay, it may overlap. So here, orthogonal frequency division multiplexing means that actually they overlap. So it's like, suppose you have Parseval's relation of two signals, and if it is zero, we have orthogonality. It could be, Y could be real. In the case, still we have conjugate for convenience. But anyway, so this is, let's define this is orthogonality of two continuous time signals. Then here goes lemma. If X of F do not overlap in the frequency domain with Y of F, then we have what? Orthogonality. Why? Because here, even though X is not zero, Y is zero. Here, Y is non-zero, but X is zero. So product is zero. So this integrand becomes zero if we have non-overlapping. However, sometimes, even though we have non-zero integrand, its integral can be zero, right? For example, suppose we have an odd symmetrical signal, then its integration is zero, right? So OFDM is actually allows overlap, but signals are orthogonal in multiplexing. So usually the spectrum looks like this. So we have some signal here, power spectrum precisely speaking, but your another signal overlaps, and your another signal overlaps in the frequency domain, but they keep orthogonality. So you can put the signals in a smaller bandwidth, retaining the orthogonality, something like that. So be careful. When you talk about FDM, frequency division multiplexing, some people allows overlapping in their definition. Some people do not allow overlapping in their definition. So be careful. Got it? Okay, what about time division? time division is related to this one. So what if when you have two signals multiplied together in the time domain becomes 0 for all t? Then definitely this becomes 0 because integrand is 0. This way, we may transmit many signals. For example, suppose you have some specific period Ts, and you divide it into 3 subintervals. And here, in the first interval, you put pulse amplitude modulated signal. That is for m sub 1 of t. So you convert it to m sub 1 s of t. Ready? So this is the one. And you have, for example, so in the second interval, every second interval, you have m sub 2 of t converted to m sub 2 s of t. These are all pulse amplitude modulated signals with pulse duration shorter than 1/3 of this interval Ts, or t if you want, right? And the third signal may be here if you allow negative value, something like that. And you have another pulse amplitude modulated signal. And as you see in this example, the pulses within each substream or sub pulse amplitude modulated signal do not overlap. Also, different signals from different messages, different PAM signals do not overlap. Then what happens? Any two of the pulses, when producted, it's 0. So you have orthogonality. Some people define time division multiplexing only this way. No pulses overlap. However, you now already know that if we define orthogonality as something like this, so even though the product is not 0, if the integral is 0, then we define it still, it retains orthogonality. Then sometimes you may have overlapping, but still you may say that it's well divided in the time domain. So suppose you use sync pulse with duration first 0 crossing exactly 1/3 of Ts. Got it? So you have first stream of sync pulses, and you have another stream, and you have, okay, something is wrong, but anyway, another stream. But they are placed in the precise position that allows this integration becomes 0 between any two pulses. Then still you can say that it's time division multiplexed signals. Right? So be careful. Now, what about code division? It's a little bit complicated and will be usually deferred to other discussions, especially in digital communication. What about space division? This is an interesting idea, and let me give you some figure. Okay, before doing that, let's see the figure to visualize frequency division multiplexing and time division multiplexing. So even though time is closely related to the frequency, if we use Fourier transform, actually we may use its variation called short time Fourier transform. What does that mean? Short time Fourier transform simply understood as you first mask the signal so that your signal of interest is within some short interval, and then you apply Fourier transform. In that case, your single signal or multiple signals can be viewed not only in the time domain and at the same time frequency domain, right? So from this short duration, one of your multiplex signals occupying the frequency domain this band. some other signal, this band, that band, that band. In that way, during the same period of time, 4 signals can be multiplexed and occupy this entire band. You may say that each one occupies different channels, something like that, right? What about in the time division? As you see that this is, for example, the period, then 1/4 is occupied by one stream, first stream, the other, second, third, fourth, something like that. Right? This is the idea of time division. And space division is related to this figure. And you've seen it from high school physics textbook. And here you have 2 sources with phase synchronism. So phase is the same. What does that mean? Usually we use 2 ping pong balls connected to a single vibrator. So when it goes up, the other goes up. When it goes down, the other goes down. So you generate the same wave front with just source separate. Then this wave, surface wave, interferes constructively, destructively. And if you have light source, then what happens? By the way, there is something like this, right? So you go down this and you view this way. This is a good product, but anyway. So you have this interference pattern. The reason is that because you have water surface, if its surface is flat, then the light passes through. If its surface goes up, then what happens? It's like concave lens. If it goes down, it becomes convex lens. So the light sometimes focuses, sometimes widespread. That's why you have this kind of pattern in your view. And not many people have noticed that. It seems that there is some line here, right? And actually, each one can be viewed as a beam in the transmission of light. And also, many of you have already noticed that using this as a boundary, we have different phase. See that? This is bright and this is dark, even though it's in the same radius, right? Why this happens? By the way, what if you have 3, 4, 5, 6 sources all synchronized? Interestingly, if you carefully choose the number of sources and the displacement between 2 sources, sometimes you may focus your power to significantly to a direct direction. And another interesting is that if you have little bit different phase, which means that your 2 ping pong balls now do not just go up and down at the same time. For example, 180 degree means that it moves this way. 90 degree means that something like this. By changing the phase angle, actually you can direct the beam. What does that mean? As if you have flashlight, which can be beamformed in an arbitrary direction by your hand control, radio wave can also be beamformed electronically. Some of you have seen from the movie or something, or actually in the military, we have radar that has moving parts. So we have some cut of parabola type or paraboloid and rotates, right? But sometimes we've seen some truck that carries some flat equipment, and actually it consists of a lot of antennas, parallel and vertical, horizontally and vertically placed, and they are what? Array antennas. And even though they do not move very fast, actually it can sweep the half of the azimuth angle and a lot of elevation angle at the same time by carefully modifying the phase of each antenna. And motivated by this idea, space division multiplexing occurred. So these two are examples. As you see, antenna separation, now antenna, not ping pong balls. Antenna separation, half of the wavelengths. And now you have how many? 7 sources. And relative phase difference between adjacent sources is 30 degrees. And interestingly, you see that most of the power, or you may say energy, is directed that way. Isn't it interesting? And here, we have antenna separation smaller, but having the same number of antenna elements. Now we have 30 degrees. In that case, the direction is a little bit more to the counterclockwise. And also, the width of this beam is widened. So by carefully choosing the antenna spacing and phase difference, you can direct your radio wave, most power of your radio wave, to the direction you want. So this may be possible theoretically. So here is the transmitter. And there are many user equipments. And they want to download many YouTube, Netflix, Disney streams. Before, in the frequency division, we needed 3 channels. 1 channel occupied for this Netflix user, this second, this YouTube, third, this Disney. But now, if you have array antenna that can steer, what you can do? You can just use the first channel. Now, first beam in the first channel carries Netflix. Second beam in the same channel carries YouTube channel signal, something like that. In this way, now you can save a lot of bandwidth. That is the idea of space division. So receivers are spatially different in the direction of departure. It can be utilized to save what? One of the most scarce resources in radio communication, the frequency or bandwidth, you may say that. Got it? So a lot of multiplexing idea tried to modernize the old telephone system. And this is one of the modern digital telephone system. So there are some levels like T1 is called trunk, T1, T2, T3, T4 channel. And as you learned in the topology of wireless network, this level means that some regional area, some bigger regional area, nationwide, something like that. So you need to put more wires together. And here, T1 has 24 voice channels, each with 64 kilobps, and they are combined. In which way? In this case, in the time division multiplexing way. Got it? So this is the time axis. And you will see that here goes the channel 1's 7 bits with signaling bit. So each channel in this case, as I told you, in T1 channel, you have 24 voices. So channel 1 to channel 24. And each one carries. So this is not a single unit height. This could carry some other bit like a 0. Okay, so 0 or 1. Anyway, 7 bits. 7 bits. So entire single transmission of 7 bits for information, 7 bits, 24 voices you require 0.125 millisecond. And you can easily compute that due to this extra F bit, your BPS is not 140 something, it's 150 something. You can compute. Anyway, so this is the way that home telephone works. The problem is that current home telephones, even though you call home telephones, are IP telephones. So this is an old technique, but some once prevailed. Finally, let me talk about vocoder, voice coder. What is the most important characteristic of our voice? Not just the simple acoustic signal, but human speech. It is generated by vocal cord, which is placed in our neck, right? We have a pipe. We have a pipe where our air flows, and we have two membranes that opens and closes this pipe. This is called a vocal cord. Okay? And this generates impulse train. And what about our mouth, tongue, and cavity in the nose? By using this, actually, we linearly time varying filter this signal. So people wanted to compress the voice. So they analyzed how it is generated. And voila, what they did is that, okay, M of t, if it is a speech signal, can be decomposed into, in a short time period, this pulse train, where you only need the frequency and amplitude and the filter. And filter, you may say that it could be arbitrary, but people have found that some discrete time filter with finite number of coefficients and whose coefficients can be easily found works well. That is linear predictive coding technique. So here you will see a lot of CELP related to vocoder. What is CELP? CELP is code excited linear prediction. As I told you, linear predictive coding is related. So you will see a lot of CELP, not S, but C in voice encoder. And still, in even 5G, we also have this generation model-based approach to compress the voice. But now our bandwidth is very large, and we may assign a lot of it. So some high definition, high quality voice do no longer employ this compression method because compression requires computation. Sometimes we need no delay, something like that. Anyway, so we are done. Oh, here goes the figure. So as I told you, we may decompose the signal into two parts, something like that. Anyway, so we are done. And from next week, we are going to cover chapter 4. And tonight, we are going to take the first midterm, the midterm exam. That's all for today.